Okay, good afternoon. Welcome, everybody. Welcome to our webinar, UKCCSRC webinar on squaring the circular economy with carbon capture and storage. My name is Mathieu Lucquiaud. I'm a professor of clean energy with CCS at the University of Sheffield. And we've got an exciting program today. So we'll start with three presentations, 3 talks, a short break, and then a further talk, and then some more discussion. So our first speaker is Dan Su from the University of Edinburgh. Then we'll have Iain Struthers, also from the University of Edinburgh. And then Hasan Muslemani, formerly from the University of Sheffield, and now the Oxford Institute for Energy Studies. What I was going to do in the first minutes whilst we wait for everybody to come online is basically give you a short overview of the project that has been funded this work, and then we'll then move on to showing the results and have hopefully an interesting chat. Okay, so effectively the project that funded this work is called newest CCS. It stands for Negative Emission in the Waste to Energy Sector, Technologies for CCUS. It was a European project, 3.5 years, who just finished in February of this year. We have partners in the UK, Edinburgh, Sheffield, SCCS, Carbon Clean, partners in Norway, Sintef, Germany, the University of Stuttgart, and TNO in the Netherlands. And effectively, our scope of work was to de-risk, demonstrate, and develop CO2 capture technologies, specifically for waste to energy plants, and also look at other aspects related to that, which that's what we'll be talking about today. So we looked at a range of technologies from various TRL. So we looked at oxy-fuel and membranes. So we had a pilot scale testing in Germany and some experimental work in Norway, looking at the advancing oxy-fuel. We had a work package focused on solvents, where we tested at 10 ton a day in a commercial waste energy plant in the Netherlands, and we also tested at 1 ton a day at the University of Sheffield. And what we're going to be talking about today, the work package on the right-hand side, a comparative technology assessment in the waste energy sector. So we'll be talking about integration, cost, business models, life cycle assessment, carbon accounting, and also assessing the potential for negative emissions in the waste sector in Europe. Project was funded by government of the UK. So the department formerly known as BEES in the UK, and funders in Germany, Holland, and Norway. And so we're grateful to our funder. And without further ado, I'd like to introduce the first speaker. So Dan Su from the University of Edinburgh, who's going to present her work on a comparative assessment of CO2 capture technology for waste to energy plant. So
first of all, thank you, and thank you everyone. And my name is Dan Su. I'm from the University of Edinburgh. And as you can see on the slides, and the topic of my presentation is techno-economic comparison of the investigated waste energy CCUS technologies. And this report is part of working package 5.3, and you can find relevant information from the project website as well. And this report is under collaboration with the project partners from the University of Edinburgh, and Sheffield, and Sintef, and University of Stuttgart, and TNO. So I just start my slides. The content of my slides is organized into 5 chapters. In the first chapter, I will give an overview of the comparison cases of basically three CO2 capture technologies and the design input. And in the second chapter, I will present the results of electricity output penalty for the 3 CO2 capture technology. And in the third chapter, I will present results of the levelized cost of electricity for waste energy power plants with the 2 CO2 capture technology, which is membrane-based CO2 capture and amine-based CO2 capture. And in the fourth chapter, I present basically 2 business models for waste energy power plants with CO2 capture. And the last chapter is conclusion. And first, the overview of key comparison cases and the design input. As you can see in the table 1, in this report, we use post-combustion CO2 capture with 35% MEA as a benchmark case. And there are two comparison types of CO2 capture technology. The type 1 is post-combustion CO2 with membrane-based, with membrane-assisted liquefaction. And in this comparison, the two kinds of membrane are used. The first one is polarized membrane. The second one is FSC membrane. And when we compare the benchmark case and type 1, because both post-combustion CO2 capture, so we assume that these two CO2 capture technologies are using the same fuel input. So we're sorry. So we're referencing the same fuel thermal input from one operational waste-to-energy power plant in Edinburgh, and that is 55% megawatt thermal input with a waste throughput of 500 tons per day. And they share the same low heating value of the fuel, which is 9.3 megajoule per kilogram. And the resulting CO2 concentration in the flue gas is the same, with CO2 molar fraction of around 11%. And for the benchmark case, we use a 95% capture as the benchmark, and because in the UK, the Environment Agencies requires the new built post-combustion CO2 capture should at least reach 95% capture rate to get environmental permit. And on the screen, the 99.72 capture rate represent to capture all the fuel related CO2. So the only 0.3% CO2 only comes from the air when combust the fuel. And because when we compare the benchmark case and type 1 case, we found that for the membrane cases, it's a bit challenging to reach capture rates higher than 90%. So we add 90 capture rate in the benchmark case as well, only for comparison. And the type 2 CO2 capture is oxy-fired CO2 capture. And the oxy-fired CO2 capture is similar like previously applied in the coal power plant. And for the waste energy, we use circulating fluidised beds as the incineration boiler, and use solid recovered fuel as the waste. SRF have a relatively higher low heating value because this waste is pre-treated, and so it has a higher low heating value. And we assume that the same thermal input of 55 megawatts is input to the waste energy power plant as well. And when we look at the CO2 capture rate for the oxy-fired CO2 capture, theoretically it can reach 100%, but because during the CO2 purification and compression process, there's CO2 emission in the oxy-fired, so the net CO2 capture rate is 94%. So all the comparison cases, we assume that the CO2 is compressed to 110 bar before transport and storage. And in the following slides, when we do the comparison, we doesn't include any energy or cost related to the transport and storage. So it's only include the CO2 capture and compression. And in this slide is overview of electricity output penalty for the 3 CO2 capture technologies. On the left-hand side is the main power requirements for the 3 technology. For the MEA cases, there are basically 3 power consumption effects. The first is electricity output penalty due to steam extraction from the steam cycle. And second power consumption is from the CO2 compression. And the third part is auxiliary power consumption, such as the boost fan and the reach and lean soft pumps. And for the membrane cases, there are also 3 main power consumption. The first is flue gas compression, and second is vacuum pumping and compression of the crude CO2 permit. And the third part is auxiliary refrigeration. And for the oxy-fired, there are 3 main power consumption. The first is air separation unit to generate oxygen for the incineration of the fuel. And the second is also CO2 compression and a purification unit. And the third part is auxiliary power consumption. In figure 1 on the right-hand side is overview of the power consumption per ton of CO2 captured. And we see that for MEA-based CO2 capture, it requires around 300 kilowatt-hour per ton of CO2 captured. And when we increase the CO2 capture rates, there's a slight increase of power consumption, but the power consumption for ultra high CO2 capture rate doesn't increase too much. And for the membrane cases, we see the power consumption for the polarized is the highest, is around 520 kilowatt-hour per ton of CO2, and for the FSC is 430. And for the oxy-field-based CO2 capture, because we didn't model in detail of the air separation units, we just design a value of the oxygen generation with ASU of power consumption of 220 kilowatt-hour per ton of oxygen. So we find that in total, the power consumption for oxy-field CO2 capture is around 40 kilowatt-hour per ton of CO2 captured. And there's potential improvements can be made in the ASU. So when like additional heat recovery can be made from the ASU aspect, so when the ASU power consumption is reduced to 100 kilowatt-hour, it can be comparable to the MEA cases. And also on the screen, I want to highlight for the membrane-assisted liquefaction, there is flexibility or the advantage of this technology because it consumes electricity, so it doesn't require, thermal steam extraction from the steam cycle. So this can bring kind of advantage when they apply it to some power plants when the thermal heat is not available, or some plants or some situation, some lower price electricity can be obtained. And in this slide is results of the levelized cost of electricity for the membrane and MEA cases. As we can see in figure 2, the membrane cases without CO2 capture, the levelized cost of electricity of the plant is 78 pounds per megawatt hour electricity. This value is already a bit higher than conventional coal-based power plants. And when the CO2 capture technology is integrated, for example, the MEA cases, the levelized cost of electricity is almost doubled. And for the membrane cases, it's further doubled to around 400 pounds per megawatt hour. So it's quite really a big increase. And I want to take a note here that the levelized cost of electricity here, I didn't include the cost of the CO2 price, and also didn't include the cost regarding the CO2 transport and storage. And on the right-hand side, because previously I mentioned there is a flexibility in terms of electricity prices for the membrane cases. So we did a sensitivity analysis when at some situation there is cheaper electricity can be obtained from the plant. So we found that when the purchasing electricity price for membrane cases is reduced to around 40 pounds per megawatt hour, as we can see on the blue dashed line in figure 3, the levelized cost of electricity for membrane cases could be comparable to the MEA cases, which is around 119 to 210 pounds per megawatt hour. And in this slide, I present the potential 2 business models for waste energy power plant with CO2 capture. And the business model 1 is also, we assume in this situation, both fossil fuel emission and biogenic emission is penalized at the CO2 price. So we want to look at what is the break-even CO2 price allows waste energy power plant to break even. That is the cost of the CO2 capture equals to the benefit it brings to the plant. And in a business model 2, we assume that in this scenario, and there's a policy support to this application. So for each ton of biogenic CO2 captured by the plant will receive a certain amount of money. We call it negative emission credits. And also there's a possibility that increasing of the gate fee is permitted. And also in this scenario, we'll assume that only fossil CO2 emission is penalized at a CO2 price of 40 pounds per ton of CO2. So in the business model 2, we want to look at what is required negative emission credit for the plant to break even. So in this slide, I summarized the results under business model 1. We see that for amine-based CO2 capture, the plant require the break-even CO2 price at around 65 pounds per ton of CO2. For the membrane cases, the price will be around 130 to 40 pounds per ton of CO2. So it almost doubles. And also, again, I need to highlight the cost doesn't include the cost of transport and storage. And on this slide, it's a result of the business model 2. And in this situation, we assume that there's possibility of increasing gate fee, and also there's possibility of negative emission credit. And on the figure 5, we can see on the left-hand side, when the gate fee increasing is 0. So this means in this situation, in a UK-based study, and the gate fee maintains at 100 pounds per ton of MSW. So the required negative emission credit for membrane cases will be around 180 to 20 pounds per ton of CO2. And for the ME cases, it will be around 65 to 70. And when there's possibility, we can increase the gate fee from 100 to 140. We can see the 41. When the gate fee increasing to 40, basically for the MEA basis, the plant doesn't require negative emission credit to make the plant break even. And for the membrane cases, when the gate fee increases to 150, basically the required negative emission credit would be around 80 to 100, and which is similar to the current CO2 price at ETS market. So our key conclusion based on the previous slides, the first is that the power consumption for the membrane cases is about 1.4 to 1.7 times higher than the MEA cases. The challenging occurs for the membrane cases for this study when the membrane cases is integrated to the flue gas at 11% molar fraction, and higher capture rates higher than 95 is challenging. And basically the choice of capture rates is a trade-off between the capital cost and the operational cost. And we found that there's a flexibility in terms of electricity price for the membrane cases. When the electricity purchasing price is below 40 pounds per megawatt hour, the levelized cost electricity for membrane cases is comparable to the MEA cases. And for the oxy-fuel combustion CO2 capture, we note there's a great improvement can be made at the air separation unit. So when there's advanced thermal integration occurred, like when the ASU power consumption is below 120 kilowatt hour per ton of oxygen, the oxy-fuel CO2 capture can be comparable to MEA cases as well. And okay, so the fifth point is the business model 1. We found that the break-even CO2 price for the MEA cases should be around 65 pound per ton of CO2 captured. And for the membrane cases, it is almost double the price. And in the business model 2, we find that when increasing the gate fee by 40 pounds per ton of MSW, the waste energy with MEA cases can break even. And if without gate fee, and then required negative emission credit will be around 81 pounds per ton of CO2 for MEA cases. So above is my report. Thank you. I see there is a question on my screen, but I don't know whether I need to continue to share my screen.
Yeah, no, that's okay. Thank you, Dan. Thank you very much. I guess yeah, you can leave your screen.
Okay.
There's a big. I can see a big black box in the middle of it. But yeah. Okay.
Okay.
Got a question from Ben Stewart, and I guess I think you've kind of answered, but for clarity, the cost of electricity quoted, were they the bid prices from producer or generation cost? So I think this is for the membrane cases. So I presume, and if I misrepresent your question, Ben, feel free to ask it yourself.
Sorry, I can't see the question now. My screen is blocked.
Well, I think it's for the membrane case, you're quoting cost of electricity.
Yes, I assume that electricity is purchased from somewhere else.
So effectively, electricity in that system, the electricity that is powering the membrane, comes from the electricity grid. And
yes.
So we were trying to show what the electricity price would have to be for the membrane system to break even with the levelized cost of electricity of the solvent-based capture system. So I think the answer was £40 per megawatt hour. So
yes,
showing that you need you need further cost reduction in the membrane technologies, I think, to be able to break even with the MEA case. Got a question from Chris Wood. My question surrounds the capture of CO2 from the process. So my question surrounds the capture of CO2 from the process. Are you capturing and storing under pressure in a separation tank prior to being subjected to the membrane capture process?
I think my answer is, like I mentioned, for this compression, we assume all the CO2 is compressed to 110 bar before transport and storage.
Sorry, Dan, I think this is, are you capturing and storing under pressure in a separation tank prior to the membrane? So I think no, the answer is no. I think you're basically pressurizing the flue gas and then putting it through the membrane system.
But the initial flue gas pressure are the same. It's basically, I think, ambient compression from the waste under power plant.
Yeah, and do you remember what pressure the flue gas is compressed to?
It's just ambient, like 1.0 bar. We assume it's ambient pressure.
This is ambient. Okay.
Yes.
Yep. Okay. All right. Okay. So if there's no further question, have you calculated the compression and transportation cost? So compression cost, yes. Transportation cost, they're not included in the numbers. Where could I find out the main impurities for each approach, membrane versus solvent versus oxy-fuel?
I'm not sure, but I think some of the project deliverable for the oxy-fuel is included in the project website. For the membrane aspect, I can't see.
So I think if you go to the project website, the project's our deliverables are available there. There's also some papers have been published by the researchers. So the work on oxy-fuel was done at the University of Stuttgart. If you drop me an email, I can send you the papers. The membrane work was done by colleagues at the University of Sintef, but it was only modeling, so there was no pilot scale demonstration. Whereas the oxy-fuel work, we had a pilot plant. And then for the solvent, there's a webinar that was done on the solvent test campaign that's also available on the website. So it's newest. If you Google newest CCS, you'll be able to find our project website. Okay, thank you. So I suggest we move on to our next speaker. So I think next we have Iain Struthers. So Iain is also at the University of Edinburgh and was also involved in the project, and he's our LCA man. So yeah, off to you.
Okay. Right, I'll crack on. Okay, so thanks everyone for coming along. Thanks for having me, Mathieu and co. So my name is Iain Struthers. Yeah, I'm at the University of Edinburgh, and I was part of the NEWS project towards the tail end of the project. And what I'm going to showcase today is the work that we did on life cycle assessment, looking at 4 different configurations of waste energy plant, two of which had CCS. So I shall crack on with that. So today, just I'm going to try and keep it high level and accessible, because life cycle assessment is, it's characterized by a lot of detail. But in essence, the kind of questions that I'm going to try and give you some insight with today are, what are the environmental impacts of a waste energy plant in terms of footprints, like carbon footprint and such like. So there's a few more that you can do apart from just carbon. How can these footprints be quantified? How does adding CCS to waste energy plant affect the environmental impacts? What are the most significant parameters of the design, or the most significant assemblies within those systems? And how certain can we be about the results, looking at uncertainty and sensitivity analyses? So my main contribution to this work was to extend this work to a full environmental impact assessment with uncertainty. And I'm also going to talk to you about 2 sensitivity analyses that we did around waste composition and the emissions intensity of electricity and heat, which is important for the results. So to make it accessible, I feel duty-bound to give a little explanation of life cycle assessment as a technique. So it's quite an established technique. It's been around for a while, and it quantifies environmental impacts, which is dead easy to say, but that is, in practical terms, enabled or made much, much easier by the existence of what we call a background process database. So this is a database that contains all of the Lego blocks, if you like, of the model that you're about to build. And those Lego blocks are called processes, and they have information on material and energy flows. So for example, down at the bottom there on the left, we've got steel sheet rolling. We've got input flows and output flows. And you can extend that all the way to this boundary between the natural world and the technological world. And any flow that crosses that boundary, by definition, is an environmental impact, either that's extractive or emittive. And if you create a jolly big list of all of the unit processes, and you characterize all of the elementary flows in relation to the footprint that you're interested in, you can work out your environmental impacts. That's life cycle assessment in a nutshell. As a process, I mean, I think I've just described it there, but you spend the bulk of your time looking at this inventory and developing that inventory. And then in terms of the things that you can do with that information, I'm sure you could understand that you can find hotspots, and we talked about the uncertainty and sensitivities, but the application of that knowledge is useful for strategic planning and policy making, particularly in this space. And it's quite commonly applied in waste management, but there's relatively few studies of waste energy with CCS in the literature. So that's LCA in a nutshell. I'm not going to read out all the bullets from this slide. I'm just going to dwell on the diagram, because it's important for understanding the work that we did. But this LCA was a little bit different to the ones that I'm used to, in that there was a real balance between the environmental harms, which is, it's quite conventional, and then environmental benefits. Okay, so when you fit CCS, you're going to have the ability to capture carbon. Okay, biogenic carbon in particular is what we're looking at, because that atmosphere, it starts off as atmospheric carbon and is drawn down into the bodies of animals and plants, and then combusted and captured, and it's sequestered to the lithosphere. So we go atmosphere, biosphere, lithosphere. That's a negative flow. Fossil carbon, on the other hand, it comes from the lithosphere to the atmosphere. And then if you draw that back down, you kind of get this like net zero in inverted commas of that fossil carbon. So that's different to the biogenic carbon in terms of accounting its environmental benefit. The second type of environmental benefit that's important and relevant to waste to energy in particular is that waste to energy plants, they can recover materials and they can also output electricity and in certain applications heat. Okay, so by the generation of those products, you can obviate the requirement for primary generation of those products elsewhere in the technosphere. Okay, so if you recover ferrous materials, in theory, you can equate that to the primary production of ferrous materials elsewhere. Okay, it's more obvious perhaps if you've got electricity, if you inject electricity to the power system, and you don't have to have as much output from your natural gas plant, then you can claim that as an avoided product. But it's important to understand those, they are not the same, although they are often, and here they are added together. Okay, so there's an important distinction. This diagram goes into what I've just described in a bit more detail on climate benefit, but you can see diagrammatically that there's all these balances of positive flows, negative flows, zero flows, and at the end of the day, that's summated to a net climate benefit. So that's what we're going to talk about in today's talk. Let's move to the model itself then. So this is, there's not much to look at, so this is my best attempt as a table. So we've got two pieces of infrastructure that were in the model. We've got the plant itself, we've got the CCS plant as well on the bottom of the table. Then we've got three life cycle phases: infrastructure, operation, and disposal. And each of the bullet points in this table, underneath that bullet point, you've got a raft of the unit processes that I introduced a few slides ago. That's called foreground data, and all of that foreground data is populated from academic literature, industrial literature, plant primary data as well. And then you can see for the eagle-eyed amongst you, we've got some downward pointing arrows, and that's those indicate the negative environmental impacts, i.e. the environmental benefits that I mentioned as well. Specifically, the plants that we considered, these are moving rate boilers, treating 500 tons of municipal solid waste per day. And we're using the MEA system that Dan described with the ultra high capture rates. So 100% of the CO2 arising from the fuel combustion. So we've still got this throughput, if you like, of the atmospheric CO2 from the inlet to the outlet. We have assumed a biogenic to fossil carbon ratio of 60%. And we've got four configurations, which I mentioned: power only waste to energy, combined heat and power waste to energy, and those with and without CCS. All of the footprints are reported in terms of 1 ton of municipal solid waste treated. And we're looking at a contemporary construction with a 30-year life. And in terms of locational specificity, we've got municipal solid waste composition from a local plant here in Edinburgh in Scotland. We've got British electricity, European heat, and global metal production for the avoided products. And to round it all off, as the system boundary was in scope and out scope, well, we didn't include waste manufacture, production, or generation, if you like. So the fabrication of the waste itself, we didn't include waste collection or transportation. That's reasonably common in the literature. And then just last diagram, system boundary, we've got the inputs on the left, outputs on the right, and then you subtract the avoided products on the extreme right. So just to give you a flavour of the level of detail that we went into. Oh, I should say as well that a lot of this analysis is informed by the energy penalty work that Dan did with the process modelling as well. So there's analytical work behind this as well to back it up. Okay, let's start with climate change results. So here we go, a data dense slide for you. So if you want to look at the dark green lines in the table on the left, you can see the breakdown between infrastructure and operation. And then you've got the 4 configurations on the right of the table. So you can start to see the differences. I've also split out the avoided products and the CO2 capture, and you can see the negative signs there to refer back to that diagram that I introduced a few slides ago as well. And what we're coming out with is that the power only system comes out with a climate impact of 155 kilograms of CO2 equivalent per ton. If you fit CCS onto that, it drops dramatically with the ultra high capture rate to -648. The CHP with no CCS is -94, and that includes a generous amount of environmental benefit from the avoided products of heat, which is usually quite emissions intense. And then you see when you fit CCS to that, again, the energy penalty, it does all work. You can fit it and still operate the plant. And this shows that you can also you can fit CCS to these plants and you don't break the climate. It's still economically viable from a climate perspective, if you like. And you can see the breakdown there with the difference of avoided products as well. They vary according to the inputs from Dan's work as well. Okay. So let's extend that just from global warming to the other environmental impacts. So we've got a whole suite of environmental impacts here, and these are all made relative to the power-only configuration, which is the sort of golden bar. So there's a few things here. Across all of these impact categories, the power-only waste energy plant does have environmental benefits in quite a number of impact categories because of primarily the obviation of these avoided products. Okay, you're avoiding average electricity, you're avoiding average heat by injection of those to the respective networks. So you do see quite a lot of benefits if you include the avoided products. Anyway, on the right hand side of the axis, you see the environmental harms. And what's important is that when you add CCS, so that's the blue and the brown bars, very rarely do you see a flip from benefit to harm. And the other important thing to say, you rarely see a flip from benefit to harm. And that's important because that shows that there is limited what we call burden shifting. Okay, so adding CCS improves climate change performance, which is what I showed in the previous slide. But generally speaking, there's very limited examples of burden shifting where you seriously impact another environmental impact category. So that's quite good news. And these are all median values. But if you look at the uncertainty, there are examples where it crosses the line from benefit to harm. But for climate change, to bring it back to climate change, they're quite far to the left in terms of fitting CCS. The uncertainty bars were well over. So again, we can be quite confident about those results. Right, I've not got long left, so I might race through this. But we've got two sensitivities that I'll present just now. We wanted to look at different scenarios of waste composition. So we altered the waste mix that we had. Major caveat here is though that we didn't account for the rerouting of those waste streams to other parts of the waste management system. So it's not a holistic perspective in that regard. But if you take out paper and card, if you take out plastic or both, or if you take out kitchen and garden waste, you can change the climate impact relative to the base case. And these are the changes. Interestingly, it was only climate impact that was really sensitive at all to these changes in waste composition. Well, I won't go into it. So this is the important bits. But basically, if you take out dry fossil carbon, i.e. plastic, you can improve your performance very slightly. And if you take out wet biogenic carbon, which you might not have expected, if you take out, because it's so wet, you can improve your performance overall, and that improves your emissions capture potential very slightly. But again, these results aren't big and they're not systemic, so it's just of interest. And then lastly, sensitivity to emissions intensity of avoided products. It's a bit of a mouthful, but if you're in a different country, or if you're in the future when your networked energy is low emissions intensity, you can use this little map here that we developed to work out the net climate benefit of the combined heat and power plant. And what we find is that if you're displacing, like I said, coal, for example, or gas, which are emissions intense, then you see you can attribute a very large climate benefit as a result of that. If you're displacing nuclear or if you're displacing wind, then you could imagine that those avoided products are much less emissions intense, so you kind of come down a little bit. And what we see is that you approach this value of around minus 550 because we haven't modelled the future decarbonisation of primary metal production, which is a thornier problem to model. So this is useful if you want to look at your country, wherever you're based, or if you want to understand in the future what might happen for the emissions intensity, the net climate benefit of these technologies. Okay, so that's everything. I think that's me time up, 15 minutes, I believe. So just to quickly skim through these last bullet points, what we found is that adding CCS to waste energy, it flips climate harm to climate benefit, and even when you exclude avoided products. And we don't see, we see limited burden shifting to other impact categories, which is good news. Also, particularly for global warming, we can be quite confident about the results. The uncertainty bounds are pretty far from the transition to positive harm to benefit. But it's really important to understand that these results include avoided products. So just be aware of that we don't over-egg the cake mixture, and that we understand how much of this climate benefit we're attributing to avoided products in this analysis and in future analyses as well. Looking at waste composition, only climate impact was sensitive to the waste composition, which I was really surprised at. But again, there's no change to the system boundary here, so we can't really draw implications of the waste hierarchy as a result of this analysis here. And as you could expect, when you decarbonise your avoided products, then your climate benefit reduces if you, as I said, include avoided products within your results. So some further work for this direction of travel, if you like. Well, there's obvious one is the system expansion to understand the waste stream management, but also I'm personally interested in dynamic biogenic carbon uptake, using other metrics, and also prospective LCA to examine what might happen in the future as energy and material systems decarbonise. So that's everything from me. I've got to shoot off at 2 o'clock, so if you want to ask questions, now's your chance. Okay, thank you.
All right, brilliant. Thank you very much, Iain. So yeah, we do have a question in the chat from, well, 2 questions. First one from Ben Stewart. How did you determine the strategic mineral impact on slide 11? So maybe if you could, yeah, go back to slide 11.
Slide 11. This one?
Well, maybe not slide 11, but how did you determine the strategic mineral impact?
Strategic mineral impact?
Yeah.
I don't think I used that term. I'm not familiar with that term. Happy to.
So Ben, you said that one. So is it slide 10? Okay.
Talk about mineral resource scarcity on slide 10, Iain.
Okay, yeah. How did I define it? I didn't define it. It's these impact categories are they're built into the software that we use. So in terms of the impact assessment methodology, that's not a level of detail that I delved into for this work. So the definitions of those impact categories, they can be found in this wealth of a body of literature on the impact assessment methodologies themselves. So I can send on some links to that, but it's not something that I looked at in terms of these weren't environmental impact categories I personally defined. These are defined as part of the software automatically.
Yeah, and these are the standard impacts that you'd seen in a life cycle assessment study.
Yes, for the recipe. This is the recipe impact assessment method, which it is one of the number of standard methods you can use.
Yeah. Okay. Thank you, Iain. And then I guess just one more question before we move on. From Stavros, Mikhailos, the heating emission calculation, what is it based on? Energy or exergy? Well, I presume it is energy. Is that right?
Pardon me, the heating? What was it?
Emissions calculation. So I guess the carbon intensity of the heat.
Ah, right. Okay. So yeah, so thermal energy exported, I think, is the line item here. So yeah, the references are just down there at the bottom. So we've got a GB electricity mix of intensity of 250 kilos CO2 equivalent per megawatt hour, and a European-wide heating mix of 186 kilos per megawatt hour. So it's no, it's not exergy. It's just electrical power or energy. Pardon me. Yeah.
Yeah, electrical energy for electricity and heat for heat. So the software that you used?
It's called SEMA Pro. I can't remember the version, but it's SEMA Pro, SIMAPRO, SEMA Pro.
Yep. Okay.
Yep.
We have a question on MOF, but I'm not going to ask you because I think it's related to your work. So okay, thank you very much. Great work. Our next speaker is
Thanks.
Hasan Muslemani, who was at the University of Edinburgh, then at the University of Sheffield, and is now with the Oxford Institute for Energy Studies.
Hi, everyone. I'll take you through the market assessment for the total negative emissions that can produce from the European waste to energy sector in Europe. This is based on some of the work that Dan and Iain have already taken you through. So without further ado, the purpose here really is to give you an idea of how much negative emissions can be captured from this sector, but I'll also introduce the methodology that we've used to assess whether a waste energy facility is retrofittable with CCS. We used a number of criteria to do this, which I'll take you through in a bit, and I'm also going to report on some of the findings of the work. So first off, we looked at the waste resource itself, and here we're looking at two things. So how much is the waste resource that we have, what the composition is currently, but how it's going to evolve into the future. And to look into the future, we used CWEP's roadmap. CWEP is the Confederation of European Waste Energy Plants in Europe. And they had developed in 2019 a sustainability roadmap that looked at what the waste resource is going to look like up to 2035. So that's what we based this analysis on. And then in the second stage, we looked at the composition of the waste in Europe. The goal really is to assess how much the biogenic content is, because this is eventually what is going to be producing our negative emissions. So this is the roadmap that I just mentioned. And something that I want to note here is that this is based on 2017 data, so there's a bit outdated. And what you see on the left here is municipal solid waste, and on the right is commercial and industrial. And there's a reason why we separated both. Something that I want to note as well, in 2017, we had around 245 or 46 million tons. This figure today is around 300 megatons. This is only for municipal waste. And as you might be aware or not, we have a recycling target in Europe of 65% of that municipal waste by 2035. There's no such or an equivalent target for industrial and commercial waste, but what CWEP did in this study is they assumed that something like that will come online. And as you can see, other parts are, some waste is going to landfill. And what we're really interested in is what is not being treated at all or residual. And this is assuming that in 2035, we're going to have 142 megatons of residual waste. And as of 2017, we had 90 megatons was the size of the waste energy fleet. That today is around 100 megatons. So if we take that 100 megatons of today's capacity, plus 11 megatons of waste that is being treated in cement co-incinerators, the capacity gap that is remaining is around 30 megatons. Something that is really important to highlight is this is an absolute estimate. We don't know if this is going to be the case, simply because of the assumptions that were made here, but also it's difficult to predict where new capacity of waste energy is going to be in the future. So I want to highlight that from this point onward, all of the analysis we did is based on the existing fleet and not on what things are going to look like in a few years. So that was on the evolution of the resource itself. And then we looked at the composition. We found that there's a lack of data on waste composition from all countries in Europe. Some of them do not report waste composition at all. But even when it is reported, it's collected and reported in different ways. So the categories that we found are being reported in the UK are different than in other countries. And because of that reason, we've decided that perhaps we should not look at the composition, at the biogenic content in the waste itself, but in the flue gas coming out of the waste incinerators as a better proxy. But then even data for that is still lacking. So to hedge against all of this uncertainty, what we've done is a bit of a sensitivity analysis, assuming an absolute lowest biogenic content and highest content, which I'll show you in the next slide. So this is a study by the French Environmental Agency in 2020 that looked at 10 different waste streams in France. And as you can see, even within the same country, the biogenic content is very different. We see that the absolute minimum biogenic content out of these 10 was 53%, and the highest was 63%. So what we've done in this study to be on the most conservative side, we assumed an absolute minimum of 50% up to 70% biogenic content. As Iain and Dan have mentioned, at times we assumed an average of 60%, but we were more interested here in a range than an average, a point estimate. This is perhaps the most important slide that I'll take you through. So what you see on the left is a reflection of that CWEP sustainability roadmap, where we have municipal waste, we have industrial waste. And what we're interested in is this blue bit, which is residual, most of which is going into waste to energy. Everything on the right is assumptions, but also we're talking in terms of emissions rather than a waste resource at this point. So if we retrofit carbon capture on a waste to energy facility or we don't, we have then two scenarios after that in terms of the destination of the final CO2. So if that CO2 is going to geological storage or permanent utilization, or if it's non-permanently utilized, and then we had to split the resource into biogenic and non-biogenic or fossil. And you can see that each one of those is going to lead to a different impact on the climate. So I'll give you a couple of examples. If we're looking at fossil content with CCS, with geological storage, and it's a fossil content, this is very much the same case as if we're retrofitting CCS on an oil or gas power plant. And so we're looking here at reducing emissions. What we're interested in is the biogenic content, which is going to lead to negative emissions. At the bottom here, without taking you through all of the details, if we are looking at fossil content that will eventually end up in the atmosphere because of non-permanent utilization, then it's leading to direct emissions. And if we're looking at the biogenic content that's going to end up in the atmosphere, that was going to be the case anyway. So we're calling that zero flow emissions, or in other words, it's emissions that would have happened anyway. So there's no net positive or negative impact on the environment. So in order to answer the question of whether a facility is retrofittable with CCS, we developed this decision tree. So the first question was, is the residual waste treated in a waste energy plant? And if the answer is no, we excluded that from the analysis. And if it's yes, the next question was, is that plant within 300 kilometers from a CCS cluster or hub? The assumption here is that the CO2 can then be transported by pipelines from the plant itself to the cluster. And if the answer is yes, we retain that in the analysis. If it's no, then we look at whether that plant is located on a coast. The assumption here is that instead of shipping by pipelines, transporting by pipelines, we can ship the CO2. If the answer is yes, we retain it. If no, then the last resort is that plant within an acceptable distance to a storage site? The assumption here is that instead of taking your CO2 to a cluster to be collected and then transported, you can take it directly to the storage site. And if the answer is still no, then we exclude it from the analysis. Everything else that has been retained on a distance parameter, we look now at whether there's enough space around the plant itself to retrofit a carbon capture facility. And I'll take you through how we did that in a bit. And if the answer is yes, then the last filter, if you may, was, is that plant large enough for it to be economically viable? And by large enough, we draw the line at 100 tons of CO2 emitted per year. So all of the plants that were retained in the analysis, I'll take you through the results here. So we started the analysis with almost 500 waste energy plants in Europe. We looked at their capacities, at their coordinates, and then we looked at all of the clusters, CCS clusters, either existing or forthcoming, and we identified 22 different ones. What you see here on the left are all of the waste energy facilities plus capacities, and on the right, all the CCS clusters and hubs that are in Europe right now. And then we plotted the cumulative capacity of these plants based on distance. So you can see on the x-axis, it goes up to 500 kilometers. And this is the total capacity of the fleet, and which, as I mentioned, was 100 megatons. So what I'm saying is most of the capacity in Europe is actually within 500 kilometers of a CCS cluster or hub. But for a more in-depth analysis, you can see that 32 megatons, or a third basically, is within 100 kilometers. More than half is within 200 kilometers, and almost 3/4 is within 300 kilometers, which is the sweet spot that we've decided is an acceptable distance. So that's what we're going to be working with, is that three-quarters of the capacity. As I mentioned, next we looked at whether there's enough space for retrofit around the plant. And what we've done here is we looked at every single waste energy plant in Europe on Google Earth to look at whether there's space around it. So we measured around how much empty space is around it. And to answer the question of whether that is enough or not, we looked at existing carbon capture facilities in the world, and some of them which are not yet deployed, but we looked at their FEED studies, their design studies, to see how much space has been allocated to them. And so we then plotted the land footprint versus the capacity. So these are examples of two of the largest projects. On the left, you see Petronova, obviously from Texas. So this is the capture facility, and we measured how much area it's taking. And the one on the right from Boundary Dam in Canada, also, we did the same. So this is the function that we've used. And as you can see, there's 7 different projects. It looks like a nice linear or almost linear relationship between footprint and capacity. Something that I want to highlight here, which is important for the next steps, is most assumptions in the waste sector is that 1 ton of waste is going to produce 1 ton of CO2. That is not always the case. As I mentioned, the waste composition can change. So the UK government and the Environment Agency have reported a range up to 1.7 tons of CO2 per ton of waste. So we've used that conservative estimate simply because the more CO2 obviously that will be emitted, that means the capture facility will be bigger. That means you will need more space around the capture facility. So to be on the safe side, to make sure that we do have enough space, we assume the absolute highest. And this is just a couple of images out of the 500 or so plants that we looked at, both from Germany, waste energy plants. You can see here, there's a lot of space around it. So we were not very worried about space. This facility is in the middle of Berlin, so there's no chance for building a capture facility there. As Dan, my colleague, has already mentioned, what we've assumed here is that we are capturing 100% of the CO2, simply because going up from 90 to 100% capture has very minimal impacts on the power consumption and on the avoidance cost of CO2. So moving forward, we assume the 100% capture. And these are the results. So we can see everything in green. As I mentioned, these are the 3/4 of the existing fleet, which is within 300 kilometers. Everything in red is outside that range. The next stage we looked at was whether those are the red ones that are outside the 300 kilometers, whether they are close to a storage site. And we found that most of them are actually within distance, except for a few. In terms of space requirements, we can see that there are 3 different levels here. So there are plants where we know that there's a lot of space, like the one I showed earlier, and that is based on an assumption that every ton of waste is emitting 1.7 tons of CO2. If it's 1-for-1, then some plants actually fit the criteria, but not all of them. So these are plants that need further analysis to determine whether there's enough space. And then everything you see in purple are plants where we know there's absolutely no space around. So we're confident there's no space. All of this is wrapped up here. So these are the headline figures. For this, what you see in green, this is the assumption that all of the residual waste that is currently not being treated in waste to energy facilities. So that's the 30 megatons of capacity gap that I mentioned earlier. If that was also treated in waste to energy facilities, we're looking at somewhere between 70 to 100 megatons of negative emissions. And what we're interested in is really the orange bits. That's the existing fleet. So if we take no CCS restrictions into account, we're looking at somewhere between 50 and 70 megatons. And once we account for all of the restrictions in terms of transport, in terms of space and plant size, we go down to 20 to 30 megatons of negative emissions, which is the headline figure out of this whole analysis. 20 to 30 megatons is what we can capture. Limitations of this work that are worth mentioning. We use a bottom-up approach to select these plants that we're going to be looking at, but these were limited to grate-fired boilers. And also, as I mentioned, we did not account for this capacity gap which currently exists, which might be diverted to waste to energy. We wanted to keep the analysis as realistic as possible. In terms of distance analysis, and this was work over quite a few months that we've done, we had to assume straight line pipelines without considering topology, without considering crossing rivers or cities or mountains, which admittedly is not realistic, but this is the best we could do at this point. So this is an area where we can improve in the future. The analysis of distance is also approximate. So we've drawn the line at 300 kilometers, but some plants might fall at 305. So, there's not much sense of why we would eliminate those. So that's something also we can work on. In terms of storage sites, the database that we've used does not have data from Finland and Sweden as well. And lastly, for space analysis, we assumed that the owners of these, or the operator of the facility, can acquire the land around it to deploy this capture facility, but that might not always be the case. We are sure that's not always the case. So there's more, in-depth analysis on each waste energy facility that needs to be done. With that, I will wrap up. If you have any questions, I do want to mention that this study, the full study, is available on the newest website, but also on the Oxford Institute for Energy Studies. And we also have a podcast which Mathieu and I have spoken on, in case you wanted to revisit any of this information. And thank you.
Okay, thank you very much, Hasan. Okay, so let me check the chat. I think yeah, we have a question. Did you differentiate between sequestration and storage in your work?
Meaning utilization?
I'm not sure. I guess well, we've assumed that the storage is permanent, that we've gone for geological storage. Sequestration, I'm not sure. We haven't looked at CO2 utilization, so effectively we're not making individual plant decision as to whether a plant should be fitted with geological storage or utilization. We're characterizing the potential for negative emissions. If you are utilizing CO2 and the CO2 is returning to the atmosphere at the end of the product, so if you're making fuel, for example, that's not a negative emissions.
Yeah.
In our
we do have examples of permanent utilization. You can put the CO2 in concrete, and that will be permanent utilization. The issue is that most of these practices are still not immature, but we don't have enough data on where those facilities or utilization points are going to be. So we didn't want to make so many assumptions. So we really limited this to geological storage sites. If that answers your question.
And second question from Ben: did you consider scalable existing and emerging carbon conversion and utilization technology in your work?
Yeah, I'll defer to the engineers on the call, Mathieu and.
Okay. Yeah. Okay. So this is not technology specific. I guess the footprint, which is one of our criteria, is based on the footprint of a conventional, commercially available solvent-based system. One of the things that we haven't looked at that you could possibly look at in the future is whether, you know, they are for the sites that are effectively space constrained, whether they are technologies that have a lower footprint, so things like liquefaction of flue gases or process intensification of post-combustion capture, things like maybe rotating packed beds or any other technology. So yeah, so we in a way meant to be technology agnostic, but we have to look at footprint, and for that we used you know, the commercially available solvent technologies.
Yep.
Okay, and then okay, and one more question. Okay, two more questions. All right, so we too are utilizing concrete and cement to sequester the carbon of our biosphere, and rightly so. This sector needs growth. A discussion point offline. Cheers, Chris. Yeah, very good point, Chris. So we'll have time for I think more discussion after the last presenter. So if you want to stay online, and then we'll happy to discuss that further. And did you consider the cost of pipeline development to connect to hubs?
We did not know.
So there's no. So we characterize the potential with our study, and we didn't look at cost of pipelines. No, if you are interested in that, there's some work out there that's been done on the cost of CO2 transport. So I'm thinking about the Clean Air Task Force as a
And zero emission platform, they have a report on cost of transport as well. They give you an indication of what different pipelines or different forms cost, but this is not something we were looking at. We were assuming that infrastructure is there, and we're just looking at whether it's worthwhile undertaking or not.
Yeah. Okay, so what else should we do? We have a 10-minute break. So yeah. Okay, so welcome back. Our next speaker is Camilla Thomson. She is a lecturer at the University of Edinburgh, senior lecturer, and she's going to talk about moving forward.
Chancellor's Fellow still.
Chancellor Fellow, okay. Moving forward, policy and carbon accounting. So Camilla was all involved in the newest project, and she actually led the work package 5, where all this work was completed. So yeah, over to you, Camilla.
Great, thank you. I just realized I was all organized and had put my notes on another screen, and they've now vanished. So that's excellent, which is very helpful. So I will have to do this without notes. So hi, this section I'm going to talk about some of the implications for policy, and what we can do about this from for making sure that we get as much. Sorry, I'm very distracted by not having my notes because I had them all set up. But the implications for policy and industry and going forward. So I also just like to acknowledge Rebecca Bell, who wrote many of the slides that I'm using today. Excellent, so it has moved forward. Right, so some of the key findings, I mean, this is really reiterating what we've just spoken about, but it was really just to kind of go back over that one of the things that we found from this project is not only is CCS on energy from waste possible, but it's technically viable, and we can actually achieve significant net negative emissions. We can completely zero out all the fossil emissions, and capture biogenic emissions. So this is all technically possible, which is great, with the net result of being able to draw down the atmospheric carbon and also potentially. There are some questions about how we actually account for the negative emissions, and further work is needed in that. So I'll talk a bit about that later. But just starting off, I wanted to start with some of the barriers to waste to energy with CCS, and where we see these as being yet. Like, why are we not yet putting carbon capture and storage on waste to energy? Well, part of this is that historically there's been a lack of financial incentives. There's been an unclear regulatory position. We've got no or limited storage facilities or storage options. And then there's also this question at the end, is it even the right thing to be doing? There's a perceived conflict with circular economy principles and the principle of zero waste, because we're potentially sending waste for incineration when it should be going back through the recycling stream. So I'm going to go through some of these. So starting off with some of the incentives, we will, here are sort of some example incentives published by the UKCCSRC, and I'm going to look at some of these. So obvious things like carbon taxes, tax or emission credits are obviously financial incentives from a policy level. And then there's regulatory requirements, financial support and government provision. I'm not going to talk about enhanced oil recovery because it's not really relevant to this talk, but that is in there as some of the work that the Global CCS Institute has found has been effective at incentivizing CCS projects. So in terms of incentives, we've got the starting point, carbon and tax credits. At the moment, the option for this is through the emissions trading schemes. So in Europe, in December, it was about 84. The emissions trading scheme was trading at about 84 euros per tonne, which works out as about £73, although that was probably on December prices, so it's a lot less now. And I should add, sorry, municipal solid waste incineration will be taking part in the emissions trading schemes in Europe from theoretically 2026, so it's looking more likely to be 2028 or 2031. We don't know whether waste incineration will be included in the UK ETS. To my knowledge, that's still not been announced. But the trading scheme is trading at £69 per tonne, or was trading at £69 per tonne in December on the UK scheme. From the work that Dan presented earlier, she found that in business model 1, the break-even price was about £65 per tonne for carbon emissions. So there is potentially a bit of profit to be made in having carbon capture and storage on municipal solid waste incineration if it's included in the emissions trading scheme and how we account for those credits. But is it actually high enough to drive this action if we're only talking less than £10 per tonne? In terms of, so that's one of the issues, and there's obviously further clarity needed about how this would fit into the emissions trading schemes, whether there's charges for biogenic or fossil emissions and how negative emissions are credited within that. In terms of the climate laws, in the EU, the new EU climate law does recognise the role of CCS in negative emissions. But in national laws, especially UK and Scotland, we're not really seeing it at the moment. Although we are sort of slightly bound by a previous EU directive. In terms of carbon removals in the UK, we've got this, the only guidance we've got at the moment is the Climate Change Act, which specifically here only considers removals as being removals due to land use change or forestry activities. There is no provision within this for carbon removals by any other means to be accounted for. So this is a question, something to look into and something to keep an eye on as policies are updated and changed. But also I'd like to point out here that this isn't just a problem for waste to energy with CCS, it's a problem for any other non-LULUCF forms of carbon dioxide removal. Going on to the regulatory requirements from an incentive perspective. So emissions regulation, the Industrial Emissions Directive at the moment doesn't really mention CCS as a best available technique for energy from waste yet, but there is probably going to be some changes on that. And we're not yet that clear on what the limits on emissions for CO2 are, whether any have been put in place. Sorry, whether any are going to be put in place at the moment. Is it possible to learn from regulations on emissions of other gases, other pollutants that have been regulated in the past? Finally, just mention of grant support. So I said that there's been historically limited incentives. However, as of a couple of months ago, certainly in the UK, there has been a big announcement of some money for CCS, £20 billion to be precise. And this has gone, well, the tier one, track one funding for CCS projects has been announced for 8 projects, 2 of which are waste to energy plants. So one of them is already hoping to capture 1 megaton of CO2 per year, and the other one is still under construction. I'm not actually sure what the value is for that. So this is some grant support. This is an incentive that has been proven to work in other countries, and we can now see it coming into play in the UK, which is great. So moving on to one of the other barriers, storage facilities. The map on the right is quite silly. All operational CO2 transport, storage and storage infrastructure in the UK is shown in green, i.e. there is none at the moment. In order to achieve negative emissions, we need permanent geological storage or potentially sequestration in cement and concrete for further discussion. The opportunities for permanent geological storage are quite limited, and there's none currently available in the UK. So there is definitely a need here for investment, not just in the CCS facility or in the carbon capture side of the system, but also in the storage facilities as well. And finally, going on to is it even the right thing to do? We are bound within waste to think about the waste hierarchy. So obviously the initial target is to minimize the amount of waste that we produce in the first place. If possible, reuse it. Only then should it go to recycling. If it's not possible to recycle or recover it in other ways, then we can dispose of it. And it's generally, we think of incineration as being disposal, but actually waste to energy fits in there as a recovery, because it's incineration with energy recovery. So it's actually slightly higher up the waste hierarchy. And the reason we need to think about this is that while waste to energy with carbon capture and storage is a form of bioenergy with carbon capture and storage, it does have an advantage in having no concerns about land use and not really needing to think about transport, because the waste is produced anyway and needs to be treated anyway. However, it is worth being aware that there is always a target to try and minimize the amount of waste we produce. So the availability of waste should, if all goes to plan, decrease over time. And we don't want to incentivize or even distort the waste hierarchy, but we certainly don't want to incentivize increased production of waste just simply to be able to use waste to energy with carbon capture and storage. But we say this, and we say, well, okay, so obviously we want the waste to be reused and then recycled before it ever comes to waste to energy with CCUS. But if the point of the waste hierarchy is about minimizing environmental impact, then what we really need to do is be aware which of these options have the lowest environmental impact. So rethinking it in the context of net zero is thinking about understanding which parts of the waste hierarchy are fossil carbon, or how we deal with fossil waste and how we deal with biogenic waste. At the moment, when we do life cycle assessments, such as the one that Iain presented earlier, the standard method of accounting for environmental impacts of carbon doesn't currently credit at all for atmospheric carbon absorption of plant-based products, because there's an assumption that this is part of the natural carbon cycle, and it's already in balance. But when we add in waste to energy with CCS, or in fact any BECCS bioenergy with CCS, we are disrupting this natural carbon cycle in a different way from the way that we're used to of burning fossil waste and increasing the release to the atmosphere. We're actually stopping carbon from being released to the atmosphere that we would otherwise expect to be released as part of that natural cycle. So this is having to rethink about the waste hierarchy. We start seeing here that where do these negative emissions actually fit in? They take place when the plant is grown, but we expect them to be released again, and under our normal accounting methods, they would just be zeroed out because of that assumption that they'll be released again within a fairly short time frame. So there's no concerns there about time delay, although obviously with trees, this is a little bit different because trees take a lot longer to grow than maybe crops and food products. Sorry, food crops. But at this point, where do our negative emissions fit? Are we avoiding emissions by actually avoiding using recycling processes, for example? When we recover the energy from waste to energy, we're actually reducing the need to produce energy elsewhere in the energy system. So are we actually reducing the amount of materials that we need to use to produce energy somewhere else, or reducing the construction needs elsewhere in the system? It becomes a very complex question, and it's one that we are still wrestling with, and we do have further work in looking into. So I went back to the waste hierarchy and I looked at this. And we look at it from the perspective of the CO2 hierarchy. So waste to energy has a benefit in that it avoids CO2 emissions from other generation technologies. The CCS reduces the fossil CO2 emissions from the waste treatment. Well, the waste to energy and the CCS, because both of them reduce they reduce fossil greenhouse gas emissions, I should say, because you're converting the methane to CO2. And then obviously, if we then capture it, capture and store is obviously a CCS process. We're achieving that. And then ultimately, it's also removing the biogenic CO2 that would have been expected to be released anyway. So there is a challenge in accounting for this correctly. And this quite complex diagram is published in several places. So I would recommend if you're interested in it, having a look at it's definitely in a report. It's definitely in at least one journal article, and it should be in in at least one conference paper. And it should be in a journal article shortly, I think, or a version of it. But the challenge here is, how do we account for this net climate benefit, taking into account the fact that this system is reducing CO2 emissions across a number of different ways, without double counting, without inadvertently increasing carbon emissions somewhere else within the wider economy. And I think the key thing from this is, because it's so complex, what we really need to make sure that we're doing with all of this work is at least being very clear and transparent in what the numbers mean and where they're coming from. So you'll have noticed with Iain's work that he reported the direct emissions reductions and the emissions reductions from biogenic CO2, but he'll also report the avoided emissions from each of these other avoided potential emissions production paths as a separate thing, so that it's possible, if anyone disagrees, or if we, as our thinking on this develops, it's possible to go back and update these values to be more accurate. So ultimately, I think that the challenge here is that we do have a system that has multiple co-products, and for life cycle assessment geeks like myself, this is really an allocation challenge. So we need to understand that we're producing waste disposal, waste treatment, we're producing electricity, heat, recovered metals, potentially reducing impacts on natural resources. We're also potentially producing negative carbon emissions, and all of these avoided emissions will change over time. So it's really important to be consistent across stakeholders and be really clear on what we're talking about. An example of this is I tend to work in the energy sector rather than in the waste sector. So I would typically look at publishing my results per kilowatt hour of energy produced. Whereas in the waste sector, the results are typically published per ton of waste treated. And actually what we're doing here is providing both. So how do you divide between them? From a policy perspective, in the UK at least, I don't know about other countries, but in the UK, waste incineration is a waste treatment activity, and all of the environmental impacts or benefits are given over to per ton of waste. But waste incineration with energy recovery is considered an energy production process, and all of the environmental impacts are allocated to the energy produced with no consideration of the fact that you are avoiding emissions from waste treatment anywhere within that process. So it makes it look as though waste to energy is a dirtier process, is a more carbon intensive, it's a carbon intensive form of energy generation relative to wind power, as opposed to waste incineration, which is cleaner than landfill, for example, as a waste treatment option. So you end up incentivizing one over the other in a way that is not necessarily useful or very valid. So these are some of the challenges that we've still got to go forward with over time. But I think the key, and we have further work to be done on the right way to account for this. And there's obviously further work to be done on how to inform policy and how to report properly. But a key thing at the moment, I suppose, is just trying to be really transparent in any work that we do, any analyses we do, and that all of the stakeholders need to try and be as transparent as possible in what they've done, so that as we work towards reaching a consensus on the right methods, we will also be able to go back and change earlier, and find consistency within earlier studies. So that's everything from me. Thank you. And I'll just go back to sharing, acknowledging all of our funders. I'll let Mathieu.
Okay, great. Well, thank you, Camilla. So if you have any questions for Camilla, please put them in the chat. I'll start with the first question from Chris Wood. ETS schemes are mainly nature-based credits, which have questionable MRV mechanics, and therefore should the VCM but striving to direct their climate finance into pre-purchasing durable, scalable CDR. Best wishes, Chris. So hopefully you can see the question too, Camilla, and try answering it.
I can see the question. I'm struggling with some of the acronyms of MRV and VCM, as I'm not so familiar with. Do you know these acronyms, Mathieu?
I can give a bit of input on the VCM. I worked in the VCM before rating different credits. So I looked at the direct air capture all the way down to forestry. And I have to say there's a trade-off between, Camilla was saying you plant a tree, it'll take a few years to grow, but then you have an issue of permanence with those solutions. They are, cheap, they are scalable, but there's a lot of issues with them. The issue with pre-purchasing CDR, as was mentioned, is that there's a limit in the supply of these projects. So for perspective, the biggest 4 or 5 projects of direct air capture in the world are looking at tens of thousands of tons of CO2, when we're actually looking at reducing billions. This is the target. And all of these projects, if you look at Climeworks and Carbon Engineering, the big 2 companies which are doing these projects, they're sold out until 2030 or 2031. So they don't even have credits to sell, even pre-purchase at this point. That's the one argument. The second argument is pre-purchase means effectively you're only going to start your climate action in 10 years once that CO2 is removed. So really the short answer is you need all of these solutions. We do need forestry or nature-based solutions simply because they are available right now, with a transition towards more durable solutions when they become available. Does that answer your question? That was it, Chris? Yeah.
Okay, and just so as a side comment, so what we're talking here about, capturing CO2 from waste incineration. effectively, so we've got 2 projects in the UK that are expected to come online in around 2027, 2028 now. It's a project in Norway that is that final investment decision, but I think is struggling with the basically the increase that we're seeing in capital costs for any equipment at the moment, post sort of a pandemic, post disruption of supply chain, and post sort of Ukraine war, or not post, but during the Ukraine war. So but that's the situation now. When these projects start operating with CCS, they offer immediate removal of CO2 from the atmosphere. The waste, the biogenic waste is it's been produced, and so we'll be hopefully seeing direct carbon dioxide removal. One of the questions in the UK that needs to be addressed is what if you're a waste to energy plant in the UK and you are doing CCS, will you be able to monetize and value your negative emissions? There is a contract that is being drafted, and it's under sort of a discussion between the industry and the UK government, and the door is not shut, but it's not open for these 2 projects to value their negative emissions. Now, if you choose to invest in a waste energy plant with CCS outside of the government contract, then you're obviously at liberty to do what you want with the negative emissions. But I think for these 2 projects anyway, the expectation is that they will have to they will only be able to value the negative emission in compliance market, and agree on the share of their revenue with the UK government. So the UK government would take a share of their revenue, and they will keep a share of their revenue, and that's I think the discussion that's happening at the moment. Okay, next comment from Steve. Hi Camilla, very interesting talk. My understanding is that some of the CO2 feeding into the HyNet CCS project in northwest England derives from waste to energy. If correct, what is the business model being used? So yes, so the business model is so the UK has 3 business models for CCS, one for power, one for industry, and one for greenhouse gas removal. Waste to energy falls under what's called the industrial capture contract, and there has been a if you like a spin-off of the industrial capture contract into a waste to energy industrial capture contract, to recognize the fact that these facilities are different from other industrial facilities. They offer waste disposal, they produce energy, which other facilities don't, and they may produce negative emissions in the way that other facilities don't. So currently that's the business model that is available to these 2 projects. Anyway, if you go on the I think DESNE's website, you will be able to see the latest update on these contracts if you're interested. And like I say, I don't think this is finalized. This is under discussion. So there's also an expert group. So if you think that you can contribute to that expert group, you might be able to join via DESNES basically.
One of the things I'm not clear of on these projects is they talk about what their negative emissions are expected to be, but they've just based it on a 50% biogenic content estimate.
Yeah, that's right.
And there is a question, like, as we move forwards, is that good enough as an accurate?
Yeah, that's right. One of the key questions is, how much biogenic carbon do you have in your carbon feedstock? I think what we're going to see, if this plant, and I presume they will join their local ETS, whether it's the EU ETS or the UK ETS, they will have to report on their fossil emissions versus the biogenic emissions. So in order to, I think they will, they'll have to pay the ETS price for their fossil CO2 emissions. So therefore, there's a very strong incentive there to say, okay, well, I'm going to measure my biogenic CO2 content very accurately. I think there are methods out there that allow you to do that. They kind of look at the ratio of carbon 14 to carbon 12 in your flue gas, but it's not something that is, if you like, we don't at the moment we don't have capability to do all the plants out there. So I think it's a section of the industry that needs to grow. And also, I don't think there's a method that currently gives you online real-time measurements. So a lot of things is it's either based on average or it's based on sort of spot measurement that where you take a sample of flue gas and analyze it in a lab a few days or a few weeks later. And then yes, the two waste energy plants in the UK. So it's the Runcorn waste energy plant. It's currently part of the HyNet cluster, and you have the Protos energy recovery facility or Protos waste energy plant, also part of the HyNet cluster. So these two waste energy projects are actually located in the same cluster.
We're not actually sure yet whether the waste incineration is going to be included in ETS in the UK. It isn't at the moment.
That's right.
It's explicitly excluded. Waste incineration. I was just double checking, but yeah, thermal input exceeding 20 megawatts definitely included, except in installations where the primary purpose is the installation of hazardous or municipal waste. But there are proposals to do it from last summer that as far as I've seen, there's been no update since last summer on that.
So I don't see any more questions in the chat. So I suggest we end here. I'm just going to add one more thing. So with UKCCSRC, John Gibbons, Abby Sanson, and myself, we're effectively working on updating the evidence that will be used for the permitting of post-combustion CO2 capture at energy from waste in the UK. So the Environmental Agency in the UK has released guidelines for the permitting of post-combustion CO2 capture plants for gas-fired and biomass-fired power station, and is about to do the same for waste-to-energy facility. If you want to look at the evidence, it's available on the UKCCSRC website. So there's a report there, and that report has gone to consultation, and we've it's not public domain. So I would encourage you to do so if you have an interest. And I think that's all I'm going to say. So thank you for attending. Very grateful to be able to share the outcome of our research with the UKCCSRC network, and hopefully see you at the next webinar. All right, thank you everybody. Take care. Bye.